Hello, my dear students. Now, this is chapter number 2 in our Introduction to Communication System course 20ELEC09I, course delivered to Year 3 Computer Engineering in the British University. Today, we are going to tackle a lecture under the title Introduction to Analog Modulation. Actually, this lecture maybe is one of our shortest lectures in terms of number of slides and maybe in terms of time duration. However, I will consider this lecture as a turning point in our understanding in the course, not only the coming chapter, which is the amplitude and frequency modulation as well as the phase modulation, but also maybe the digital modulation part of the course. So now, please allow me to start sharing my presentation. You can see it here and start our first lecture or our second chapter, in this module. Okay, now I believe you can see my presentation, and this is chapter number 2, Introduction to Analog Modulation. Allow me please to start operating my laser pointer and start going into this chapter. Okay, if you remember in our previous lecture, we were dealing with what's called the Fourier transform and Fourier series, or generally what's called the frequency domain analysis. We started the lecture with a very quick flashback on what we call the Fourier domain analysis. And after that, we also scan the Fourier series part. We study in depth what's called the Fourier transform. Also, we tackle the Fourier transform properties. And finally, we grow up to the system level where we study the convolution, and we can now understand the relation between the convolution in the time domain and the multiplication of frequency domain, or vice versa. If you remember, one of our examples, or maybe the main basic example in this lecture, were this rect transformation into a sinc function. Here we have studied that whenever you have a rect function in the time domain, you will have a reflection in the form of a sinc function in the frequency domain. But why I'm now showing you this signal again? As you can see, this signal is a symmetric signal around zero frequency. This is what we call the zero frequency, or the DC frequency. And this is a signal symmetric around the zero frequency. Okay, no new information after that. If also you remember, and still you can access this actually over your e-learning, we also make some demo using a MATLAB where we start to record some voice and play this voice over the time domain, as you can see here in the upper graph. And after that, we start to convert this voice into frequency domain where we get something like that. Also, we make a similar test when we start to change the frequency of a sinusoidal and hear the voice, if you remember. Again, another frequency spectrum located around the zero frequency. So, again, what is the conclusion? The conclusion is, whenever you are dealing with a physical signal in a time domain, I mean a real signal in a time domain, it can be a video, a photo, an audio, or whatever, you will get a spectrum which is somehow localized around the zero frequency. We will call such a spectrum what we can call the baseband signals. So, by definition, the baseband signals are those signals located around the zero frequency, which is the normal Fourier transform for any realistic time domain signal. Perfect. Then, where is the problem? We have baseband signals. Where is the problem? Okay, let's turn to the communications. And without being an expert in the communication, I can easily tell you that we can distinguish communication systems into two main types of systems. But let me first remind you, what is a communication system? A communication system is some sort of data or information transformation from a transmitter to a receiver. So this transformation process, this delivery process, can be either in a guided medium or a non-guided medium. For example, the link between your satellite dish on your roof and your receiver is a guided medium communication, because your satellite dish, or mainly your LNB, is connected with a coaxial cable, and this coaxial cable is elongated till it reaches your receiver, and then you have the transmitter and the receiver. So this is one example of a guided communication. We have a lot of examples for a guided communication. For example, our under cable telephone network, whenever you are making a call between two landlines, so it's a guided medium, a guided medium communication. In the past, it was using a twisted pair, but now it's turned to be an optical fiber. So we can have some examples related to what's called a guided medium communication. No problem. I believe up till now you cannot reach it, the overlap or the common ground between what I did say in the first 2 or 3 slides when I'm talking about a baseband signal, and what is the relation between this and what I'm saying now related to the guided and non-guided medium. But let me go on. So this is a guided medium example where you have a physical dedicated medium. What I mean by dedicated, that only your signal is transmitted over this medium. The cable extended from the roof to your receiver carries only your signal. So that's why it's a guided medium. Guide your waves or guide your signal till it reaches your receiver. So this is simply an example for a guided communication. But on the other hand, of course, this is easy to mention a huge number of examples where we have an unguided medium. Your mobile phones are unguided medium. Your Bluetooth connections, Wi-Fi connections, all these stuff are unguided communications. Okay, no problem. No, but let's turn to the issue. Let's turn to the problem. Is what if we are dealing with an unguided medium, and all of us sending our voice over a channel? All our signals are located on the same frequency spectrum or the same frequency portion. All our voices or sounds are located within the same band, as we already see in the first lecture when we make this scanning over the sinusoidal signal. So all our voices are in the same band. What if all of us start to convert this signal into or convert our voices into an electronic signal using a mic, and then all of us then transmit this over an unguided medium? Simply, what will happen? What's called interference. All signals located in the same frequency portion will interfere together, and the receiver will not be able to distinguish your voice from my voice, because simply both are on the same frequency band. So, as a conclusion, you can never use such a baseband signal over an unguided medium, because simply this baseband signal will interfere with other baseband signals, and then the receiver will get nothing. Then what is the solution? How we can overcome such a problem? How we can overcome such an interference problem? The solution is simple. This is our baseband signal, as I described. It's a signal located around the zero frequency component or the DC frequency component. What if, my dear student, if by a way or another, I get this signal and then I shift it to another frequency? Okay, then how you solve, or how such shifting solves a problem? Simply, I will say to you that for each application, for each application, I will send or I will dedicate a certain frequency, as you will see later. So, for example, for those people who are dealing with mobile communication in a form of a 4G, using a certain operator X, they will have a certain frequency band localized for them. However, those are hearing radio in a form of an FM radio, they will have another frequency band. So for each application, you will have a frequency band. But now what you have implemented this is you shift your baseband signal to be what's called a passband signal. Simply, this is what's called a modulation. So the modulation is simply to carry, to shift your frequency, your baseband frequency spectrum into a certain frequency operator using what we will call later on a carrier. So this is simply describe how we perform modulation, or on another way, we did not answer the question how. Actually, we answer the question why we are doing a modulation. So simply, we are doing a modulation in order to convert the baseband signal into a passband signal to escape from the interference problem that will occur if all of us send a baseband signal. Now, then the question will be how you will make this process, how you will convert this baseband signal into what you call a passband signal. This is actually a critical and an important question. Okay, my dear students, so now the question is how you will implement such a magic shifting to this from this baseband signal to this passband signal. Okay, this is simply the model of our communication system. You have the input message. Now you have what's called the modulator, which will shift the baseband, which will shift the baseband signal into a passband signal. Then this signal will go over the unguided channel medium, and then at the receiver, you should have what's called a demodulator, which will return back the signal from being a passband signal to be again a baseband signal, and then you have the output transducer or whatever it is. So this is basically a general block diagram for an analog communication system. Maybe by the end of this lecture, I will show you the difference between an analog communication system and a digital communication system, where there is only one block is the main difference. Okay, so this is a process. This is the overall system. Again, if you remember, I told you that by changing this operating, or what we will call later on the carrier frequency, you will change the working band. So let's have a look overall over different bands. Here you will find everything you hear about: gamma rays, X-rays, ultraviolet rays, visible, infrared, microwaves, and radio frequency. This is everywhere over every frequency. You can change your frequency, you will get different signals. Mostly in our communications systems, we are dealing with ultraviolet, visible, infrared, microwave, and radio. For example, your mobile phones are working in radio frequency. Your satellite communications between between the NALSat, for example, and your satellite dish is a microwave communication. Your remote controls in your home is an infrared communication. This small infrared transmitter in your remote and the LED detector in your TV or air conditioner or whatever is a receiver. Also, we have what's called an optical communication. Here we have a huge amount of application for such an optical communication. Maybe satellite communication is also one of the optical communication applications. Let's go more close to this interesting area, which is the RF, the radio frequency, and the microwave frequency. So this is an example for different application where you have your FM radio, your analog television. I don't know, I believe that most of you maybe never hear about the analog TV, but somewhere 10, 20 years ago, we were mainly operating using the analog TVs, these VHS and UHS, or very high frequency and ultra high UHF and VHF, sorry, very high frequency and ultra frequency. We have our mobile signals. We have a lot of signals here. You can see for this different spectrum covering the RF and the microwave region, which is of course a very interesting region for communication engineers. So this is a spectrum. So now the next question will be how, or we're still thinking of how we are doing such a modulation. So in order to answer the question how we will do this modulation process, let's define the inputs and the outputs for this modulation process. So we have an input message. This is the input, or maybe my voice, maybe a video, whatever it is, live streaming or whatever it is. So this is the input signal. And now this input signal is an analog signal, by the way. And we have what we will call the carrier. This carrier is the frequency at which I would like to shift my message into it. Again, the frequency which I would like to shift my message into it. And we have the main block who will perform this task, who will shift the signal from a baseband signal to a passband signal. And finally, you have the out, which is the modulated signal. Again, we are still searching with the question how we should shift this task. So in order to answer this question, let's turn back to this important slide, where we have the input and output. Actually, this is somehow a very tricky exercise. In the previous, maybe in your signals course, or maybe even in our previous chapter, I give you a signal and a tool. I told you, yeah, for example, this is a rect signal. I need to make a Fourier transform, and then you search that the output is sync, for example. So this is very somehow normal. Or maybe in our previous chapter, actually in the end of our previous chapter, if you remember my these students, I told you that we have an input signal and we have a low pass filter. So you have the input signal and you have the process, which is a low pass filter, and please draw or determine the output in the time and frequency domain. But now the question is somehow different. I give you the input and the output, and I told you, please think about what is the process to be implemented to turn this input to that output. This is very interesting. So we have now to search for the process at which this baseband signal is transmitted to be a passband signal. Okay, this is somehow, maybe it is not so easy job, but it's a doable job. So let me now return to my very simple whiteboard. I believe you can now see it. So, and let's stop sharing. Okay, and let's search about that. So what we have is, this is the frequency, and this is the input. This is the message. Something located around the zero frequency. Okay, perfect. You need to do some hidden information to get something like that. So this is what's called FC, or the carrier frequency. Of course, you have a similar, we already have agreed that Fourier is a symmetric even function mathematical transformation. So we have a symmetric, of course, due to my very bad drawing, this is not symmetric, but realistically it's symmetric. So try to believe me. Now we have this, how we can use this chat. So in order to answer this question, you have to be somehow an A student in your signal system previous year course. Why? Because in this course you have been learning some important mathematical operator called convolution. In the convolution, which is, if you remember, we already have implemented a good revision. Maybe I believe it's a good revision when we deal with systems. So, for example, for an output g of t, the convolution is simply the integration between negative infinity to infinity for x of tau x of tau h of t minus tau d tau. Sure, if you remember. So can I write this in the frequency domain? Of course, yes, because convolution is a mathematical operation. We usually know that mathematics can be implemented everywhere. If you remember in my previous lecture, I told you that we can apply Fourier transform on time domain, and also we can apply it on spatial domain. If you remember when we deal with MS processing, so mathematics can be implemented everywhere. It is not restricted to time. So you can say that g of f is equals to, again, integration from negative infinity to infinity. Let me call it, for example, x of f dash h of f minus f dash df dash. Again, remember, my dear students, my important term, dummy variable. Here, f dash is a dummy integral variable. No worries. So again, where is the proof? Where is the solution? Okay. What if you replace this h of f function with what we call a delta Dirac function? What if you replace this f function with a delta Dirac function? This delta Dirac, you know, the delta Dirac has a certain value. So, for example, when I say, let me make it here, for example, when I say delta f node, that means I have a delta function at f node. Very simple. Usually the amplitude of delta is 1, otherwise you mentioned, and this is the location of, this is the location of f node. So what I will say is that this is delta fc. That means that this is a frequency, it has a delta at a frequency called fc. Okay. So what I'm going to do now is that I will replace this the h of f by delta fc. Let's now rewrite the integration. So g of f is equals to integration from negative infinity to infinity x of f dash, of course, I'm sorry, delta of fc minus f dash df dash. Do you remember this from your signal class? That's why I mentioned I need an A student in signals. So do you remember this? When you have an integration between a delta function, and a signal or any other function from infinity to infinity, the output of this integration is simply x of f minus fc. So simply, this g of f is a shifted version of x of f to a frequency fc. So let me keep. So if simply this is x of f, the input signal around the zero frequency, after this convolution process with delta at fc, the output simply will be a shifted version of this x of f, this is g of f, it will be a shifted version of this of this x of f at a frequency called fc. And typically, this is a modulation process. You shift the baseband signal to higher frequency called fc to become a passband signal. That's what we call a modulation process. Perfect. So now, after doing this shift, what we have concluded, we have concluded the following, that this is our input message, m of t. But you will stop me for a while and tell me, no, you are wrong. We are not dealing with a time domain, my dear. We are dealing with a frequency domain. So this is in m of f. Okay, you're right. Then, what you have did as an operation, it's what's called the convolution. And your carrier is a delta function at fc. And then this is the output, which is s of f, or the modulated signal. This is simply the block, but this is in the frequency domain. Okay. Are we able to shift it back to the time domain? Of course, yes. We are now expert with Fourier transform and inverse Fourier transform. So we can easily shift frequency domain into time domain and vice versa. So let's do it. Okay, so let's refresh the process. This is the m of f, an unknown message. And this is the output at fc and at negative fc. This is s of f, or the modulated signal. What you are going to do in between is that you are going to multiply by this fc delta, and similarly in the negative frequency spectrum with the negative fc delta. So if you make a convolution between the input message and these two deltas, you will have this modulated signal s of f. So this is what's called c of f, or the carrier in the frequency domain. Now, I'm very sorry. Okay, now let's do it to the time. This is a dummy input, any time domain input. So this is simply in my voice, something like that. Any m of t. Don't worry. Any message. Then, this convolution process, remember, the last part of our chapter number 1, convolution in one domain is a multiplication in the other domain. So please don't forget, here we have a convolution in the frequency domain, so we have multiplication in the time domain. In our previous chapter, we make it in the other round. So we have, if you remember, a multiplication in the frequency. So it becomes a convolution in time. Now we use the reverse direction. We have a convolution in the frequency, so we have a multiplication in time. Very simple. Do you know what is the inverse Fourier transform of this signal? Of course you know. I am 100% sure that you know. This is the very simplest, the most simplest frequency domain we ever see. This is a sinusoidal signal. And of course, this is, we will know later, this is a modulation signal. So, what we have concluded from this example, my dear students, is modulation is a convolution process in the frequency domain. So, it's a multiplication process in time domain. Carrier is a 2 delta function in the frequency domain. So simply, it's a sinusoidal signal in the time domain. Again, for those who have attended our first extra session, discretity in the frequency domain cause periodicity in the time domain. Just a hint for the A+ students. And then we have this multiplication. So by the end of the day, let me return to my presentation, please. So by the end of the day, this modulation process is a very simple process on time domain. It's just a multiplication, like that. You just multiply the message with the carrier, and that's all. You didn't do more than that. So multiplication is a key parameter in doing modulation. In the next, maybe in the next part of this lecture, I will do two very important mathematical examples. As usual, please remember, these mathematical examples are not only for hands-on experience, but also for taking observations. What we are going to do is very simple. We know already the carrier is a sinusoidal signal, but let's start with the very most easy message. We only have a single tone message, a monotonic signal. And the carrier is, as we described, is a sinusoidal signal. Let's describe mathematically what will be the output in both time and frequency domain. This will be directly the example that we will start with in our part number 2 in chapter 2. So for that, thanks you very much. This is the end of part number 1 in our chapter 2 lecture. See you later on in part number 2.